I am borrowing the lecture from Charlie, who was who gave this lecture in Thailand. So I will be just going through that lecture. And then if you have any question, please stop me, because this is supposed to be an introductory and interactive. You can ask the question in Bangla or English, doesn't matter, I understand both. And we'll try to help you answer as best as we can, okay? So first question, molecular dynamics. If you haven't heard the term, by the end of the lecture, you'll understand why, what it means. But the first question is like, why do we do it? Okay. So, you know, if you look into an atom, there is actually nice, I should have got the video. It's called Power of 10. The Power of 10, this video came out in the 90s or something, where you can, is an animation of you zoom down by a factor of 10, what do you see? And as you can zoom down and zoom down and zoom down, finally you'll come to see an atom. An atom is always jiggling and wiggling because of the temperature. The only time an atom is frozen if you go to T equals to 0, like minus 273 Kelvin, right? So in the biology, in your cell, every time an atom is always fluctuating. You always have some kind of kinetic energy, okay? And that kinetic energy makes us actually living, like, you know, how well tuned those kinetic energy in a biological system. So to understand something at an atomic level, we have to somehow account for how the different atoms are fluctuating. And the way you calculate that is the field called molecular dynamics. There are other ways you can calculate, but the most popular and most efficient one now up to now is the molecular dynamics. So, so the answer is like, if you want to replicate the thermodynamical effect of small molecules, how they're fluctuating inside our cell, we have to do some kind of molecular dynamics. And the molecular dynamics, this is, you know, it has been called a computational microscope, okay? So in computational biology, you'll see certain terms as name called omics, like bioinformatics, you know, whatever omics you can think. And then there are like other part of computational biology, molecular dynamics is one of them. There's a fundamental difference between them. Omics is you already have the data and you are going to find a pattern in the data. And then the data are coming from experimental observations. So that's omics. And molecular dynamics falls on the other part. It generates data where the experiments cannot. Like it fills out the gap where you know, we do not have an experimental technology to generate those data. So it fills out the gap in a microscopy. So if you go in a microscopy, you have you have a light microscopy, and then if you go further, you have X-ray. Then if you go further, you have electron microscope. But if you want to go even further, then you do not have any experimental tools to look into a live molecule jiggling and wiggling. And that's where the molecular dynamics comes in. That's why it's called a computational microscopy. So there is a fundamental difference. Here you are generating data as if you are doing an experiment. In an omics, you already have the data, then you are looking for a pattern in there. Okay, so so again, like, you know, these are models that tries to generate the data. So how do we do it? We have to be very faithful to the physical laws so that we can generate a physically relevant data. A good review, this is actually is a nice review, a molecular dynamics simulation for all. It didn't come out too long back, 2018. So it has most of the updated stuff, and it's very well written. So, you know, when you get time, read it. I'm not sure if I put this paper on the Slack. If I haven't, I'll put this paper up. And to all of you, please follow the Slack channel. Please communicate via Slack channel and so on. That's how we are going to communicate now and communicate after the workshop. So be active on the Slack channel. Now, why people do MD? Okay, let's see. Well, if you're doing, and this is so true, as a lot of people come to me and say, like, I know if I do this MD, I'm going to find the drug for this cancer, because you're hoping like something amazing will happen out of the MD simulation. Okay, and this is so common. I hear it so many times. And if you want to say like my protein aggregates, I want to see how my protein aggregates. And, a lot of things that if you, like there are a lot of things like you know experimentally like something will happen, and you come to try to design an MD simulation. But these are not hard to, these are not easy to design. So if you want to see something amazing, that's one reason. The other reason, most of the time you'll be doing for this, okay? Because this is the more reliable part that you can do. So, which is like you predict your thermodynamical quantities. Okay, because MD is easy to replicate the thermodynamics to an MD simulation, like binding affinities. So that's like, you feel like, nothing amazing is happening, but that's actually more reliable, robust way to do. You can do stuff on the left. That's a lot of work. There's a lot of knowledge of statistical mechanics is required, and you have to be careful. But people do it for both. It's just I'm putting the expectation most of the time, you'll probably do stuff on the right, on the left. Yeah. So when you do an MD simulation, and we'll do it today, what you are expected to see is you are expected to see a molecule in motion. It's like a movie, where you have snapshots of the molecules at different pace. And if you put them together, it will be like a movie. It's really a movie. Okay. However, what that movie corresponds to is, if we do everything right, how that molecule behaves in a solution in a real life. Okay, so that's what we are trying to do. And you can connect those to thermodynamics. We are not going to go into details of thermodynamics, but if one of you, if you have to discuss about it, I can discuss. But the hope is, there is an ergodicity theorem which says, like, if you watch a molecule, a single molecule long enough, for infinite time, then if I have an Avogadro numbers of molecule in my solution, then I can find the behavior of thermodynamical behavior of those Avogadro numbers of molecule by just watching one molecule long enough. So that's the philosophy behind it, that we are going to watch a single molecule long enough so that we can replicate the thermodynamics behavior in the simulation, in the water, in real life. So motivation is, if you want to see something happening, but if you are trying to ask the question, I just want to run the MD to see something happen, that's not a motivation. That's not going to work. So you just think about MD as an experimental tool. Just because it's cheap doesn't mean that you're just going to do it. Okay, if your lab had the constraint on the money, and you say, like, I want to study how the genetic variations in Bangladesh among different people, something like that, you're just not going to start picking up people from the road and have a genetic sample, right? You have to have a experimental thought and setup, and then you start, because sequencing costs money. So you have to think same way. You're just not going to start an MD simulation because you have the computer and think like, let's see what happens. Nothing will happen. You have to have a careful experimental plan to see, like, how can I make an experimental plan so that I can see something happens in the MD simulation. Okay, so how it works. So in MD simulation, what we calculate is the force between two atoms. And then here, the atoms are very stylized, in the sense the atoms are very, we made a lot of approximation what an atom really is. But let's say if atom looks like a simple sphere, okay, for now, atom doesn't look like that, but let's assume. So if an atom looks like a simple sphere, if we do not have any other force on it, then Newton's second law, it has some velocity is going to just keep moving on, right? Until another atom comes in. And another atom comes in, so it can have multiple different ways. It can collide, or most of the time it will have an attraction. It will bend its path and so on. Okay. So that is the thing that what we do in MD. We do a time series of how different atoms are interacting with each other, how different atoms are, having force, providing force to each other. Okay, so we start with the initial setup of atoms, and we see, and we provide them some kind of velocities, and then let's see how they insert force on each other over the time, and we look at that time series. So that's the data that they're going to come out. You're going to see how different atoms are behaving in the presence of each other. So yeah, we start with a set of initial positions. We give them an initial velocity. We calculate the force, then move the atoms according to the force. Then we go back to the step again and repeat it. And typically, each steps are calculated as of the order of 1 to 2 femtoseconds, but there can be a larger time step. Like we calculate first what will happen at 0th time, then what will happen at the 2 femtosecond time, and what will happen at the 4 femtosecond time, and so on. But there are techniques to do it larger, but typically it is done at 1 to 2 femtoseconds. The reason is that's the vibration frequency of hydrogen. So you want to capture everything. So hydrogen is the fastest thing that's moving, is the lightest. So you want, that's the time step that we choose there. But there are other ways to go around it. Okay, so we have the initial velocity, and we said like we update as the force go on. But how do you update? So if ideally you should calculate the force, but if you are not from physics background, force is a very messy thing to calculate because it's a vector. Vector always has 3 dimensions, and you have to calculate the angles, and you have to calculate the so on. So instead, what do? You calculate potential. Potential means like it's a scalar. It just, you don't have to understand all of it. The bottom line is like, it's easier for bookkeeping purpose to calculate potential. And then force can be easily calculated from potential by taking a derivative. So even though our goal is to calculate the forces, but for bookkeeping purpose, we'll be using a potential. So from now on, all the terms that you'll hear the term potential. Okay. The whole idea is like we want to calculate the force, but it's easy to do it through the potential. So an example is like if I have 2 atoms, carbon and oxygen, if we connect it by a spring, if I measure the force, if you have a spring, the farther you go, the force is bigger. If you have in the what you call equilibrium position, no force, and then if you come closer, the force is again bigger. So that's what the force is like. It's a negative force because whichever direction you want to go, is want to pull you back the other direction. That's the spring. And then how far you go from the equilibrium. So, but it's easier to. Okay, so that's the force. Basically, it says the negative term means like it will be, wherever you want to go, it will pull you back. That's what it says. But it's easier to calculate this term and carry this term. And whenever I need to calculate the force, I just take a derivative. So that's why we carry the potential. So now in molecular dynamics, you don't have to understand all the math, but and a Nobel Prize was given for this. Okay, so that's not easy to come to the understanding for it. So, but let's understand what's happening, right? As I said, like I want to replace a experimental observation to molecular dynamics calculation, right? So I have to be as much accurate as possible. The most accurate way to calculate is quantum mechanics. But using quantum mechanics, you can calculate, there is a size limitation, how many atoms you can put in a quantum mechanical calculation, and also how much time it takes. Is typically you can do 1,000 atoms. It takes, weeks to calculate the forces between 1,000 atoms and so on. So we don't do quantum mechanics. So we have to do some kind of approximation where the quantum mechanical force can be approximated by our Newton force, like springs and bonds, like, connected by a spring and so on. And these are the terms that you see it on the right, okay? So the term that, and these, even if you don't understand all the physics, but just remember the first term is like if two atoms are connected by a bond means like an electron is being shared between them. So if the two atoms are connected by a bond, then they cannot go too far, like they will be stuck. Depending on single bond and double bond, they're very stuck to each other. And we can approximate that by putting a spring with the proper strength. Again, this kind of potential, wherever you see Kr squared, that's a spring potential. That's like a spring. Okay. Angles, similarly, is in a sense like in your protein molecule or in biomolecules, the angle between two atoms, they can, there are certain preferable angles. And again, you can have that at a spring, like put like imagine like if you have like two atoms, like 3 atoms, and you can put a spring between them, then these 2 atoms angle will be like, can vibrate around that mean value. So that's like a spring in the angle direction. This is a little bit complicated. It's called dihedral when you have 4 atoms, then how the 4 atoms can rearrange. And then you have electrostatics. This is electrostatics. And then you have something called van der Waal interaction. What it does is it makes sure 2 atoms do not sit on top of each other. So those are the 5 kinds of major forces that you are going to see. But there is a lot of physics goes on determining these values of Kr, K theta. That means like what will be the strength of the spring and what is the optimal value where there will be no force. There's a lot of physics go behind that, and we'll have a lecture later today. So the idea, running a molecular dynamics simulation is very easy. You put your computer, the computer spits out. But to develop that, to come to that point, a lot of work goes how we can transfer a quantum mechanical force calculation to this simple Newtonian mechanics force calculation, and how we can derive these constants. And that's where all the physics goes. Okay. So, so we'll not be developing any force field. That's called a force field, like where you derive all these constant, but we'll get a peek into the force field so that we know what goes into when you run into an MD simulation. So how it works. So, as I said, we start with the position, we start with the velocity, and we iteratively calculate how each other puts force on each other, and we see how a molecule evolves. And then from those things, we can predict different properties of the system. Okay. But again, as I said, just remember, before you can start, there are so many values of the constant that we need to be derived, and it has been done by other scientists for us. So we are going to borrow from their work, and we will use them. There is currently, okay, so this part maybe I should reiterate very well. Currently, because of the requirement of the computational resources and the power that we have, typically you can run a system for a microsecond. That will be a typical, and that's like if you have access to supercomputer for like 3 months, 4 months, and so on. So typically a microsecond. The richest people, they can run in milliseconds. There are some companies in USA, they can run in milliseconds. But a biology can happen in seconds and hours. Like when you're seeing a biology, that means like if the two molecules come, do they interact or not? And they can interact over the time period of seconds or minutes or so on. Okay, some can interact at the time second of microsecond, but there are not many. So remember that time scale. If you are going to run an MD simulation, you're going to say like, I want to see these two molecules are going to dissociate. You might be disappointed because after 3 months, 4 months, you are running 1 microsecond, but your biology happens in a second or in a minute. Okay, so that's not a proper question to ask the MD simulation, to design an MD simulation experiment. Okay, so you have to be, so if you want to just see the brute force way to see the biology by MD simulation, currently we do not have this capacity. How do we do it? That will be our next lecture, where what we do is like, as I said, somebody has already developed the parameters for us. We're going to take those parameters, okay, and those parameters, when somebody has developed us and put this in a nice library or format, that's called a force field. There are a few different kind of force field. We are going to use those force fields, and then somebody else has made a software that will take the force field, that will take your protein and calculate the steps and calculate how the molecule evolves. That's got an MD engine, like molecular dynamics engine. So there will be 2 parts. So molecular dynamics engine, all it does is like, you have to give it a initial position and velocity of a molecule, and you have to give it a force field, and it's just going to calculate the forces one after another, and so on. That's the molecular dynamics engine. That's all it does. You have to provide the force field and the molecule. And the force field, what it does is like, it develops, in a force field package, it develops all the constants that you have to develop through all this physics. So we will run an MD engine, and we'll see some of the parameters in the force field. Some of the popular MD engines are Amber, Gromax, Charm, and if it is not confusing enough, it's also, they have their own force fields. So some force fields are also named Charm, Gromax, and Amber, and so on. Okay, so it's a little confusing. So so that these 3 has their MD engine as well as force field. And then but there are other MD engines who, they're just MD engines. They use the force field developed by others, like NAMD. I think we probably will have NAMD. We will work with NAMD during this week. Well, I'm going to skip that in the sense like I told that before. You have to have a good design of computational experiment before you start your MD. Otherwise, you are not going to get result. And a good design typically starts with having a structure, either an experimental, or we'll learn in our modeling part. You can calculate a structure from AlphaFold. And then once you start with a structure, like in case of a experimental structure, sometimes you'll have missing atoms. So we add the missing atoms. And then we add solvents, because everything in our cell, there are solvents there. Those are the typical steps. And then we find parameters from the force field library. Like, okay, I have my atoms. What are the parameters? And then we put it into an MD engine and we run MD. And I think that's in our next lecture. And then finally, they analyze the data. So again, running an MD is the easiest because there are 200 scientists around the world. They have developed the force field for us. There are another 200 scientists around the world. They have developed an MD engine for us. All you have to do is like click, it's going to run. That's the easiest part. The hardest part is to analyze it. Because if you do not understand what you are doing, you cannot understand. You will just have, and there are so many papers comes to me for review who just ran MD and say like, I saw these, I saw that. And I reject all of them. Surprisingly, half of them still get published. I do not know how. But but really, if you do not design an MD experiment, well, you are not going to get anything out of it. So because remember, like an MD just can add most a microsecond worth of data. your biology happens in seconds, minutes, and hours. So there is no way you can run and see MD simulation. So I get to see the biology. There is no way you can do that. So you have to design your experiment so that you can get the best information out of MD simulation. And that's where the analysis part comes. So, yeah, I already said that the actual part, running the MD is the easiest part. It's like analyzing the data and correlating with the experiment. That's where your understanding of science will come. So our take-home message is like the simulation can give us, insight between the physics and chemistry that goes to the atomistic level versus the biology of Avogadro numbers of molecules that we see in an experiment. So it's going to connect those two. And then, like when I started my postdoc, I was happy to run a simulation. Like I first published my paper in PNAS. I had 20 nanoseconds of data. That's like 5 copies. So altogether 100 nanoseconds. I was saying I have 100 nanoseconds of data. Nowadays, people throw away 100 nanoseconds of data because they can run like a 1 microsecond. So as the computers are getting faster, our accuracy is getting more. The people, we can do more. Okay. So it's an exciting time there,